Welcome to Multivariate Calculus. Today we are going to explore a fascinating and incredibly useful concept known as the total differential. If you have ever wondered how scientists and engineers predict the overall behavior of a complex system when several different parts are changing all at once, you are in the right place. We will build this idea from the ground up, starting with a simple real world analogy, moving through the mathematical formulas, and finally applying it to calculate measurement errors. By the end of this session, you will have a deep understanding of how to analyze multivariable changes. Let us start by imagining you are hiking on a mountain. You want to know how much your elevation will change if you take a small step forward and another small step to the right. Your total change in height depends on two things: how steep the mountain is in the forward direction and how steep it is to the right. If you multiply your forward step by the forward steepness and your rightward step by the rightward steepness, you can add them together to guess your new elevation. This simple idea of adding up small changes from different directions is exactly what the total differential does in calculus. It is a mathematical tool that calculates the overall change in a system when multiple different parts of that system change by a tiny amount at the very same time. Now that we understand the hiking analogy, let us look at the formal mathematics. In multivariate calculus, a function often depends on two or more independent variables, like z equals f of x and y. When the input variables x and y change by very small amounts, which we call increments, the output variable z also changes. We define the actual exact change in our function as delta z. This formula simply says that the change in elevation is the new height minus the old height. Delta z represents the true change in height on our surface. Delta x is the small change in the x direction and delta y is the small change in the y direction. Calculating this exactly can be very difficult for complex functions, which is why we need to look for a reliable approximation. Since calculating the exact change is difficult, we use the concept of partial derivatives to create a linear approximation. A partial derivative measures the rate of change in one specific direction while keeping all other directions locked in place. If we assume the changes delta x and delta y are extremely small, the curvy surface looks almost flat, like a tangent plane. In this approximation formula, the partial derivative of f with respect to x is the slope in the x direction. The partial derivative of f with respect to y is the slope in the y direction. We multiply each slope by the size of the step taken in that direction and add them up. This gives us a very good estimate of the true change delta z, and it is much easier to calculate. This brings us to the core concept. We take the limit as our small macroscopic changes become infinitesimally small, approaching zero. We replace the macroscopic changes delta x and delta y with the microscopic differentials dx and dy. This gives us the official formula for the total differential, dz. The term dx is the infinitely small change in x, and dy is the infinitely small change in y. The partial derivatives act as our scaling factors or slopes. As dx and dy get larger, this linear approximation gets worse. But for tiny microscopic changes, this formula is incredibly accurate. It tells us exactly how much the function's value will shift based on the tiny shifts in its inputs, summing up the individual partial changes. Let us visualize what this formula actually means geometrically. On your screen, you see a three-dimensional coordinate system with a curved blue surface representing our function. At point P, we have drawn a flat gray tangent plane that just touches the surface. When we move a tiny amount dx along the x-axis and dy along the y-axis, we can look at the change in height. The true change on the curved surface is delta z. However, the change in height along the flat tangent plane is our total differential, dz. You can see that for very small steps, the flat plane is extremely close to the curved surface, making dz a fantastic approximation of delta z. This visualizes how we replace a complicated curvy surface with a simple flat plane. Before we move on to real-world applications, let us see this with a concrete mathematical example. We want to find the total differential of the function z equals x squared times y cubed. To do this, we need to look at how the function reacts to changes in each variable independently. First, we take the partial derivative with respect to x. We treat y as a constant number, so the y cubed term just sits there, unaffected. The derivative of x squared becomes 2x, giving us 2x times y cubed. Next, we take the partial derivative with respect to y. This time, x is treated as a constant. The derivative of y cubed becomes 3y squared, giving us 3x squared times y squared. We now have our two independent rates of change. Now that we have our partial derivatives, we write down the general formula for the total differential, which acts as our master template. We will substitute the two partial derivatives we just calculated into this exact equation. This step combines our independent rates of change into one unified equation. Replacing the terms gives us dz equals 2xy cubed dx plus 3x squared y squared dy. This is our final algebraic answer. It tells us exactly how a tiny change in x and a tiny change in y will combine to create a tiny change in the overall function z. If we knew the exact numerical values for the starting point and the step sizes, we could plug them in to get a single number for the change. This formula we just saw leads us to an important real-world application, estimating measurement error. In fields like engineering and physics, systems rarely depend on just one variable. When manufacturing parts, machines always have a tiny margin of error in multiple dimensions. The total differential is the backbone of error analysis. It allows engineers to predict exactly how small errors in individual measurements stack up to create a larger error in the final product. By using the total differential, we can ensure that these small combined errors do not cause the final product to fail. Furthermore, this approach is much faster and more efficient than calculating the maximum possible volume and subtracting the original volume from scratch. To see how error analysis works, let us look at a specific geometric formula. We are going to estimate the maximum possible error in the calculated volume of a cylinder. The volume of a cylinder is given by the standard formula V equals pi times r squared times h. Here, V represents the total volume, r is the radius of the base, and h is the height of the cylinder. If our measurements for the radius and the height have slight errors, those errors act as tiny changes, dr and dh. We will use the total differential of this volume formula to estimate the resulting error in the total volume. To do this, we will need to find how sensitive the volume is to errors in each specific measurement. Let us set up our problem. We are given a cylinder where the radius is measured as 2 meters, with a possible error of 0.05 meters. The height is measured as 5 meters, with a possible error of 0.1 meters. First, we calculate the partial derivative of the volume with respect to the radius r. Treating height and pi as constants, the derivative of r squared is 2r, giving us 2 pi r h. Next, we calculate the partial derivative of the volume with respect to the height h. Treating the radius as a constant, the derivative of h is just 1, leaving us with pi r squared. These derivatives represent the sensitivity of the volume to changes in radius and height. Continuing with our calculation, we set up the total differential formula specifically for the volume equation. The term dV represents the estimated total error in the calculated volume. We substitute our calculated partial derivatives into the equation. The first bracketed term is the sensitivity to radius changes, and the second is the sensitivity to height changes. Now we have a complete algebraic model for the error. dV equals 2 pi RH dr plus pi r squared dH. We are finally ready to plug in the specific numbers given in the problem. We will replace r with 2 and h with 5 for our base measurements and replace dr with 0.05 and dh with 0.1 for our maximum possible errors. Let us perform the final arithmetic. Substituting our values gives us 2 pi times 2 times 5 all multiplied by 0.05 plus pi times 2 squared multiplied by 0.1. We simplify the terms inside the parentheses first. This gives 20 pi times 0.05 plus 4 pi times 0.1. Multiplying these out makes the individual contributions very clear. The radius error contributes 1 pi cubic meters of error, while the height error contributes 0.4 pi cubic meters. Notice that even though the height had a larger measurement error, the radius error impacts the volume more because the radius is squared in the original formula. Adding them together gives a final estimated error of 1.4 pi cubic meters. Let us summarize the key takeaways from our exploration of the total differential. First, the total differential is a powerful mathematical shortcut for calculating the overall change in a system when multiple inputs shift by microscopic amounts at the same time. Second, it works by using partial derivatives to create a linear approximation, essentially replacing a complicated curvy surface with a simple flat tangent plane. Third, while it is an approximation, it is highly accurate for infinitesimally small adjustments. Finally, this predictive power makes it an essential tool for error analysis in engineering, physics, and economics, allowing us to ensure that small combined errors do not lead to system failures. You now have a solid foundation in analyzing complex changing systems.